Okay. Good evening, everyone. I'm Nilmoni Karak, a research scholar at IIT Kharagpur, and I'm the PMRF NPTEL TA for the course Fourier Analysis and its applications. And yeah, so this is live season 6, and today I will discuss some problems related to your week 6 content, and first we will review what we have learned from week 6. Okay, so first we have seen a formula of a formula of Srinivasa Ramanujan. Okay, we all know about Ramanujan, and who has a big amount contribution in number theory. Okay. Okay, so the formula is basically mm, the Fourier transform of uh, gamma square. Okay, minus infinity to infinity gamma a plus it exponential minus it I dt equals to equal to root pi gamma a plus half time cos hyperbolic minus 2a I by 2, and a is less than 0. Okay, and through this formula one can find Ramanujan, a messenger of mathematics, and 1915 cited in GHRD collected papers, volume 7, TTFF. Okay, and so yeah, using Starling formula for gamma function, and then using okay, so gamma square we can write gamma a plus it times gamma a minus it, and then using beta function, so we will estimate this integral. Okay, and finally we can find this. Okay, using using duplication formula for gamma function. Okay, and okay, then we will see uh, next class. We have seen Sturm-Liouville problems and PDs. From sorry. So we all know, right? 1 cos x sin x cos 2x, sin 2x, and so on. Okay. Hmm. Sin 2x, these are like this forms a orthogonal system. Forms and so on. Forms an orthogonal system. But yeah, it is interesting to know. Is there any other orthogonal system exist? Yeah, mm, some special orthogonal system exist. So on L2 minus 1 1, we have the sequence of legendary polynomial, that is P naught x. So we will see what is P naught x, what is pkx. Okay, P1x. Okay, P1x and P2x, that form a complete orthogonal system. Okay. Yeah. So apart from these, also if you know on L2 R. Okay. So the family of Hermite function functions provides a complete orthogonal system. Okay. So let us see what is orthogonal system. Okay. So definition. Orthogonal system. Let H is a separable Hilbert space and B equals to phi 1, phi 2, phi n, and so on. Is an orthogonal system of non-zero elements in H such that the linear span. Linear span means like this ck, the sum ck phi k. Okay, of B is tens. So, do you know what is separable Hilbert space? Actually, separable means it has countable uh, tens subset. Okay, so tens in H, and uh, if this thing holds, then B is called orthogonal system. Okay, in H. Okay. Okay. So, for example, you just consider this Hilbert space minus pi to pi and consider 1 cos x, sin x, cos 2x, sin 2x, and so on. This holds your orthogonal. This provides an orthogonal system. Okay. Not only orthogonal, complete orthogonal. Okay. Okay. So is it clear, right? What is orthogonal system? Hi, Ravi. Yeah. No, 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 no. That is different actually. Yeah. So here the basic thing is similar, but like two element PM and PN. So orthogonal in L2 means so in L2 norm. So they are like inner product space. So this like phi 1, phi 2, and so on, right? So phi m comma phi n, that is 0, okay, for m not equals to n. Okay, then like it is called orthogonal. Got it? Hmm. Yeah, m not equals to n. Yeah. So basically here in L2 norm, right? So if you see for this one time cos x and whole square, because L2 norm should be square, right? And minus pi to pi dx. This should be 0. If you check, so cos square x, right? Cos square x means so half minus pi to pi 1 plus cos 2x. Okay. My is it correct? And L2 norm it should be right. Mm, cos square x. So half 2. Okay, this is 4. That is okay, no problem. But 2, no, this is 2. But 2 cos square x means 1 plus cos 2x, right? What? Okay, okay, okay. That should not be 0. Yeah. Yeah. Uh, yeah. Actually, this course has a very less number of registration. Yeah, very less number of registration for this time. Yeah. Yeah. So now if you see but under L2 norm it should be right. Yeah. Hmm. Yeah. Actually, see one thing. Am I? Sorry, I was correct. I was right, but something is different little bit, because this orthogonal system is not only this phi m and phi n, so also you have to multiply uh, some weight. Okay, that's why. Okay, so minus pi to pi, and then if you do square dx, then if this is 0 for m not equals to n, then it is orthogonal. Okay, now to show it, so you have to choose a suitable omega x. Okay, not only phi m and phi n. Okay, so orthogonal system. So you can add, like you can multiply. You should multiply. You should have just you have to multiply this weight. Okay, okay. So did you check all videos? Okay. Otherwise, little bit difficult, right, to understand everything. Like this is advanced course. Yeah. And okay, but if you check, I think you can easily uh, because yeah. uh, Yeah, actually, one thing, I made a mistake. Okay, yeah, actually, yeah, right. No, yeah, inner product means basically L2 minus pi to pi with the inner product f comma g. This is minus pi to pi fx comma gx bar tx. This is the inner product. Actually, I was taking the whole thing square. Okay, so that's why I got stuck. Okay, so now, yes. Now, if you do like between 1 and cos x, right? So 1 and what is the cos x bar? This is cos x and dx. So this is, this is 0. This is 0. Now, only cos x, this is 0. And similarly, minus pi to pi, 1 sin x, this is also 0. This is, and also you do cos mx times sin nx dx. This is also 0 for m not equals to n. You can check. So half 2 so cos a sin b formula you use, and then something sin a plus b sin a minus b, and yeah. So yeah, that's how you can check. This forms a orthogonal. Yeah. Now got it right. Oh, and yeah. So now some theories there. Okay. Um, so I think you know about Bessel function, legendary polynomial. So you did you hear, like, did you know this kind of function, Bessel function? These are special function, right? Yeah. No, do you know what is legendary? Okay. I'm say, like, asking you. Do you know about legendary polynomial and Bessel function? All those you have seen in your BTech course. Yeah. That's why I'm asking. Okay. So okay. Okay. First let us discuss the legendary polynomial. Okay. Yeah. So this legendary polynomial already I have like told you yeah. So this P naught x, P1 x, so on. This forms an orthogonal system. So or moreover, this forms complete orthogonal system. Okay. So first, how to introduce this legendary polynomial? First, you have to know legendary equation. Okay, legendary equation is nothing but a differential equation. Legendary equation. This is also you know how to solve, right? Power series method plus p into p plus 1 y equals to 0. You know, right, how to solve this differential equation. So you know, like the solution looks like this n equals to 0 to infinity n x to the power n. Okay, and so using power series method, you can yeah, you can find the solution. Okay, and the solution basically a naught times. Also, since this is a differential equation, so it will have some and homogeneous. So C1 fx plus C2 gx. Okay, and and actually, so the solution looks like this, and solution is p minus 2, p plus 1, p plus 3 divided by 4 factorial x to the power 4 minus dot dot and plus a1 times x minus p minus 1 p plus 2 x cubed by 2 factorial plus p minus 1 p minus 3 p plus 2 p plus 4 x to the power 5 4 factorial minus dot dot dot. Now, can you write this in compact form? Okay, so uh, and if you write this in compact form, and from this actually the legendary polynomial is derived. Okay, yeah, ha, yeah. You have to look at this. Okay, yeah, but but like the legendary polynomial is exactly not same as this. Okay, so but this is this is a particular case, legendary polynomial. And legendary polynomial should satisfy this solution. Okay, okay, yeah. So yeah, constant we will manage. Okay, this a0 and a1 we will manage. Okay, so we will see. Uh, so so what we consider. Okay, we will see. Okay, very soon we will see. So pkx, this polynomial, basically it should be is a polynomial is a polynomial. So polynomial so it should have a degree, right? Polynomial of degree k, and pkx satisfies the legendary equation 1 minus x square pk double dash x. That means what? So this is a particular solution of this differential equation, right? pk dash x plus k into k plus 1 pkx equals to 0. And third condition should be, so pk1 is 1 for every k equals to 0, 1, 2 and so on. Okay. Okay. And so since I already told you these forms P0, P1, P0, P2 and so on. So this P0, P1, P2 and so on. This forms an orthogonal forms a complete orthogonal system. So uh, this theorem should be there, right? If K not equals to L, then your PKL and PKL not PKL, PKX and PLX, okay, are orthogonal. That is -1 to 1 PKX PLX dx equals to 0. Got it? Okay. And next, if you show, if you want to see how this form a complete orthogonal system, then like you have to use some Oyster approximation theorem. Okay. But so but it is difficult to like to observe this, to see this. Okay, now like this is something like abstract type. So, but there is some Rodriguez formula. Rodriguez formula. Just Rod, yeah, Rodriguez. Yeah, not integral. Okay, this is. I think this is. You are saying this is different. Okay. So this formula says actually Pnx can be written as like this. Okay. So nth derivative. Okay, x square minus 1 to the power n. Okay. Okay. Pnx can be written as like this. Okay. So this formula has some properties. Okay. So n plus 1. This formula like satisfies this recurrence formula. So you can say recursion or okay. Pn plus 1 minus x time 2n plus 1 Pn plus n Pn minus 1 equals to 0. Okay, so so just put the value Pn plus 1, Pn minus 1 and Pn, all those values, so you will get okay. X. Okay, now one interesting thing. So from this formula, can you find the leading coefficient? So this is a polynomial, right? So this is a polynomial. Pnx means this is polynomial. So something like a0, sorry, a0 plus a1x plus a2x square plus dot dot an x to the power n, right? So the x to the power n. So can you find this an? Okay, let us check. So pnx is 1 by 2 to the power n factorial dn dxn x square minus 1 to the power n. Okay, what is the leading coefficient? So leading coefficient of p in x. Okay, that is, see, first constant you can take outside 2 to the power n factorial. Like this won't affect, right? Uh, and LC means just leading coefficient. dn dx, and dn means n derivative. Okay, and x square minus 1 to the power, yeah, nth derivative, yeah. So you are like taking n derivative of this function x square minus 1 to the power n. Okay, so see one thing, the leading coefficient for this polynomial x square minus 1 to the power 2n and the leading coefficient of x to the power 2n both are same, right? Yeah. So just observe it. Leading coefficient of dn dxn x to the power 2n. Okay. And now you can derivative this nth time. Okay. So the derivative should be first 2n, then 2n minus 1. First 2n times x to the power 2n minus 1, then 2n minus 1, and then 2n minus 2, and so on. And finally, n plus 1. Nth derivative should be n plus 1. Okay. And okay. Okay. And then you're like, so, and then 2 to the power n by n factorial. And this is, this is your leading coefficient, but you can write it like this 2n factorial and 2 to the power n, and here, so this is, if you multiply n factorial in numerator and denominator both, square, yeah. So this is the leading coefficient actually. Okay, now we will try to see one thing. Question is, what is the square of the L2 norm of Pnx? Okay, so L2 norm means this we want to calculate. Okay, and okay, so let us see. And Pnx is what? Pnx is 1 by 2 to the power n into n factorial dn dxn x square minus 1 to the power n. Okay, so one thing, yeah. So for simplicity, so we want to calculate this. Okay, Pnx, because we want to calculate the square, right? So the inner product should be Pnx comma Pnx. Here m equals to n. Okay, yeah, that is only norm Pn, na, norm Pn square. That is only, and we want to calculate this. So for simplicity, we multiply first 4 to the power n means the square, 4 to the power n and n factorial square, and integration minus 1 to 1 Pnx square dx. Okay, now just calculate Okay. So Pnx is this. So Pnx square is this. So this and this cancel. Cancel. Okay. Cancel out. Got it right. So just you will have minus 1 to 1 dn x square minus 1 x square minus 1 to the power n dn x square minus 1 to the power n dx. And dn means your nth derivative. With respect to x. With respect to x. Okay. So now your answer is no. So answer should be in the function of n only because you see here you are integrating with respect to x. So yeah. That's why that's yeah. Number means of course dependent on n only. Yeah, dependent on n. Yeah. Yes. So we must now repeatedly integrate by parts. Okay, so you have to use by parts. So then, yeah. I will write it and transfer all the derivatives from the second factor onto the first. Uh, yeah, actually in lecture video also we did earlier. Okay, to establish the orthogonality of the sequence of polynomial dm x square minus m x square minus 1 to the power m. Okay. Okay, so let us do it. Okay. Uh, how to do it? So this is equals to actually minus 1 to 1. Okay. So you have to integrate once and differentiate once, right? And first integral in parts, first integral that should be integrate minus 1 to 1, and that will give your some constant, right? Some constant like so bypass. So first fix it. This is first function and this is second function. And if you integrate this, so you will get one constant term because so you are taking you are integrating with respect to with respect to x, and upper limit is 1 and lower limit is minus 1. So you will get one constant and minus 1 to 1. And first see, so you are taking this is first function and this is second function. Okay, so anyone because both are same, so that's why you can take anyone. So one time you are integrating, so that's why dn plus 1. No, not sorry, not integrating. So you are differentiating. First function you differentiate, right? So minus integration dd of first function. So that's why you are differentiating. And if you integrate this, so then dn minus 1, x square minus 1 to the power n dx. Okay, got it. And but what is b1? b1 is where b1 is dn x square minus 1. Just you one time you are multiply. You are so sorry. You are taking integration. Okay. So n minus 1 x square minus 1 to the power n and minus 1 to 1. Okay. How to calculate this? You immediately you cannot put x equals to 1, x equals to minus 1 because you have to differentiate first, right? Okay. So, but this function fx equals to x square minus 1 to the power n has plus minus 1 as roots of multiplicity what? Multiplicity what? N, right? And all the derivative of f up to and including order n minus 1 must vanish at plus minus 1. And this implies, see, so it as roots of multiplicity is n, and then all the derivative of f up to and including order n minus 1. So up to this n minus 1, at least n minus 1, okay, must vanish at 1 and minus 1. Okay, so for this only, for dn minus 1, so if you like, if you derivative n minus 1 times, so you will have some function that is like that function vanishes at plus 1 minus 1. Okay, so that's why this b1 is 0 only. Okay, got it? And so this is 0 minus this. So that's why it should be right. So see, now we want to like integrate this by parts again. Okay, by parts again. Okay, so we want to use by parts again in this integral. Okay, and similarly, so you will have um, so minus and minus positive, and also again you will have some constant. Okay, for this part, for this part only, for this part only. Okay, so first you integrate so like I am saying fx gx dx, you know by how to by parts, right? Minus 1 to 1, so minus 1, uh, so gx time fx dx, so basically yeah, gx integration minus 1 to fx and minus 1 to 1 and minus 1 to 1 d gx dx minus 1 to 1, okay, fx dx dx. This is the rules for by parts, right? Rules of by parts. And so that's why, so this implies dn plus 1 dn minus 1. Okay, this implies dn plus 2 x square minus 1 to the power n and dn minus 2 x square minus 1 to the power n dx and something constant. Okay, and constant similar reason with for similar reason this constant will be vanished. Okay, and this is 0, and okay, and so on. Okay, and this so on, and finally what we will get, so you have to apply again and again by parts. Okay, you will have minus 1 to the power n, so this sign is like changing, right? First minus 1, then plus 1, and then so minus 1 to the power n will come, minus 1 1, and so if you do n times, if you do n times, so I am doing n times. Okay, this iteration. Okay, so d2n x square, so n plus 1 n plus 2, so when we are taking second times by parts, so then we will have we are getting dn plus 1 n plus 2 second time, so n times d2n n plus n, and then and if you do n times integration, then you will have dn minus n means x square minus 1 to the power n dx only. Okay, okay, because now one thing you know how to derivative it, you know. Okay, so d to the power 2n x square minus 1 to the power n equals to d to the power 2n x to the power 2n, because lower term remainings are lower term. So the highest term is x to the power 2n. Okay, and x to the power 2n minus if you derivative 2 to 2n times, that will be vanished. So we are taking only this term, and this is just 2n factorial. Okay, and then minus 1 to the power n minus 1 to 1 2n factorial x square minus 1 to the power n dx. Do you know how to derivative this? How to differentiate this? So this is x square minus 1. This is even function. So minus 1 to the power n 2 time 2n factorial 0 to 1. So we can write 1 minus x square to the power n. Uh, okay, because in 0 1 we can write. Okay, um, yes, because we want to keep it positive. Okay, so 2 times 0 to 1 1 minus x square. Uh, yes. So yes, you are right. You are right. So plus n also, right? Yes. So then 2 times 2n factorial 0 to 1 1 minus x square to the power n dx. Now you know how to calculate it, right? Mm, so x square equals to u x square. That is also, but I think simply you can do also. Uh, yes. You are right. You are right. But for half, yeah, sorry, 2n, right? 2n factorial and 0 to and see here also the limit will remain same. Okay, it will remain same and 1 minus u to the power n u to the power minus half du. Okay, and you know how to what is the value of this integral. So for this you have to know the beta integral beta pq greater than 0. You know about this 1 minus u to the power p minus 1 u to the power q minus 1 du. So from this is actually 2 2n factorial. Oh, also one thing, this 2 and this 2 cancel. Okay, so 2n factorial beta n plus 1 comma half. Okay, and this beta function has some special formula. This is gamma p, gamma function, gamma q divided by gamma p plus q. Okay, and now what is this? So 2n factorial gamma n plus 1 gamma half gamma n plus 3 by 2. So 2n factorial, this is gamma half root pi. Okay, root pi, and gamma n plus 1 is basically your n factorial and divided by gamma n plus 3 by 2. And also you can write this like 2n factorial root pi n factorial divided by uh, okay. Mm. So this is n plus 3 by 2 is n plus half plus 1. So n plus half, then n minus half, and so on 3 by 2, 1 by 2. This is. So your so we started this from this. So for to the power n and in factorial we multiply it. Okay. So minus 1 to 1 pnx square dx. So 2n factorial root pi n factorial and here for to the power n, for to the power n and n factorial square, n factorial square and n plus half, n minus half, so on 3 by 2 half. So 1 n factorial and 1 okay is cancelled and yeah, finally 2n factorial and 4 to the power n, okay, and times n factorial. Hmm. Okay, see here if we here how many terms half minus half 3 by 2 okay, how many terms are there? So 0 0 to n, right? 0 to n, so n plus 1 terms, right? So this you can multiply by this 2 to the power n, 2 to the power n minus 1, not n minus 1, sorry. So this is 2 to the power 2n, right? 2 to the power 4n means 2 to the power 2n. So 2 to the power 2n minus n plus 1, and this will become 2n plus 1 factorial. Okay, how? Because you just multiply by 2. 2n plus 1, so 2 times 2n plus 1 is 2n plus 1. 2n minus 1, 2 times 2n minus 1 means 2n minus 1. Okay, and this is 2n, so 2, this is, divided by, okay, okay, one thing. 2n plus 1 is there, and one thing, something. Oh, okay, 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 okay. So gamma half is also there. Okay. So if when you are splitting gamma n plus 3 plus n plus 3 by 2, so last in the, at the end gamma half. So gamma half equals to root pi, and this cancel. Okay, and 2n plus 1, and here okay, this is your, yes, yes, and this is 2 to the power inverse, so beta function actually for calculating we are like getting, so yeah, here this is we are representing this as beta function. Yes, 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 yes. So yeah, so finally we are getting, yes, 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 yes. Yeah, yes, and also some so legend more problems on legendary polynomial, so some properties. Okay. Uh, so we will like solve some of them. n plus 1 to Pn plus 1 dash. Dash means your derivative, okay, and n plus 1, a first derivative, yes, x square minus 1 Pn dash minus nx Pn plus n Pn minus 1 equals to 0 for Pn plus 1 dash minus Pn minus 1 dash minus 2n plus 1 Pn equals to 0 and 5x Pn dash minus Pn minus 1 dash equals to n Pn, and finally suppose x to the power n equals to n cj pjx, then cn is 2 to the power n factorial all that is what already we have done. So this is basically leading term. So yeah, so from this we will have, because the leading term is different when so the this is the mm, uh, 1 by cn is your leading term, okay, for pjx. And so how to get, see, in 6 x to the power n, right? So you know the leading coefficient for the pjx is leading coefficient of pjx, pnx is your 2n factorial to the power n factorial square, just we have seen, okay. So to make this x to the power n, so your coefficient should be 1, overall coefficient, so cj, so cj, so cn should be 1 by leading coefficient of pnx, and this is nothing but 2 to the power n factorial square to n factorial, okay. Okay. mm, Now what we will do, we'll solve some problems, okay, related to your, so do you, so you are doing you are like trying to solve assignment problems, okay. So are you able to do it, or you are taking help from somewhere? Yes, but sometime in like sometime just I solve some problems related to assignment problems, not same problem, okay. But still from there you can get some ideas, okay. Okay. It's depend. It depends because uh, some day, yeah, some week. I don't know. Actually, every day different person join. Okay. Yeah. No, IIT Kharagpur. Okay. Yes, yes, yes. Yeah. Faculty. Yeah, yeah, yeah. Okay. One simple question. This is in also assignment, not the same problem. The value of 100 p 101 minus 1 plus 99 p 100 equals to. Please try to solve. Just take 30 second or 1 minute, and I am giving a solution. Okay. S is there. Any idea? Yeah, properties, but here is a similar thing. So simple thing. Yeah, not because they are all involved. So yeah, here all the identities like about derivatives. Okay, some recurrence formula or recursive formula. Okay, and include the derivative of first derivative of Pn. And here the derivative is not involved, right? Yeah. So this is already I told you, right? When we defined the legendary polynomial for all k equals to 0, 1, 2, and so on, right? And this is given. So pk of x equals to 1 by 2 to the power k factorial, and this is a kth derivative x square minus 1 to the power k. Okay, so what is pk of minus 1 then from here? So that's why we should write like it, not 0. You are putting minus 1 directly here. So that's why you are getting 0. You cannot put exactly. Yeah. So this is but you can put here only. Okay, you can put here only. So minus 1 x to minus x means so minus 1 to the power k will come. So that's why minus 1 to the power k will come, and remaining all the things should be same. So that's why this is minus 1 to the power k time pk, also x equals to 1, and since okay, that is not, so minus x, and you can remove it. So pkx, and from here pk minus 1 is minus 1 to the power k time pk1, and pk1 is what? This is 1. So this is minus 1 to the power k. So you are getting pk1 is 1 and pk minus 1 is minus 1 to the power k. So now your question is, so 100 times p101 minus 1 plus 99 times p101. So this is 101, right? So minus 1 to the power 101 and plus 90. So this is 1. So this is minus 1. So minus 100 plus 9. Yeah, minus 1. The similar type problem is in assignment. Okay, you can check. And next problem, the square of L2 norm of P50x on. Now only we have done. Right. Is it doable? No, 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 no. X, not 1. We already have seen, right? Just proved it, right? See, here we already proved it. So just put the value of n. So, okay, 2n plus 1. So here n is 50. So P50 2 divided by 250 plus 1. So 101. Okay, got it. The question was the square of L2 norm of P50. So square of L2 norm. Okay. And next question, yeah, 2n plus 1. Yeah. This is what you will get from those 6 properties. 300. Got it? Any idea? Oh, your voice is breaking. Okay, 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 okay. Uh, yeah, the properties were like pk dash 1. This is your k plus 1 by 2. But how? That is what we have to see. pkx equals to x. Just I am writing the formula again and again. Okay, so what is the derivative of this pkx at 1? So 2 to the power k and k factorial, this is constant. Okay, so what you have to do? dk plus 1, dx k plus 1. So you are differentiating again, right? X square minus 1 to the power k at x equals to 1. Okay, so what you will think, so this x square minus 1 to the power k, so you just x square minus 1 is what? Sorry, what happened? Okay, just to give me 1 minute. Something is wrong. NGZ FKC IFCO. Just 1 second, huh? Okay, now it is visible. Okay, so x square minus 1 is what? X minus 1 to x plus 1, right? Now you write here only. And then you do what is the derivative of fg. So f g g dx plus g dx, right? And but one thing is here, like, yeah, differentiation by part. I, no, one thing. You derivative, okay, that is correct, right? You derivative. So what you want to do? What? No. So you want to derivative dx k plus 1 x minus 1 to the power k x plus 1 to the power k. But see one thing. So how many times you are differentiating? K plus 1 times. So you are so that is so k plus 1, choose 1 will be there. Okay. K plus 1 times 1, and then your differentiate your dk dxk x minus 1 to the power k and ddx x plus 1 to the power k. Okay, and this is 1 by 2 to the power k factorial, k plus 1 1, and this is like same as dk dxk x to the power k, and this is this is k time x to the power k minus 1, and also at 1 we are differentiating. So this is what? This is k factorial. So 1 by 2 to the power k factorial, k plus 1 1. So this is k factorial. This is k time, and this is k. So x equals to 1, at equals to 1 1, and x equals to 1 1. So this k and k cancel. So k plus 1 and k. Okay. Oh, sorry. So this is not correct. Yeah. So this is k time x plus 1 to the power k minus 1. So this should be 2 to the power k minus 1. And this 2 to the power k and this 2 to the power k minus 1. This is 2 only. So finally, k into k plus 1 divided by 2. Oh, okay, so pk dash 1 is your k into k plus 1 divided by 2, and we wanted to calculate p100 dash 100 times 100 plus 1 divided by 2. So 50 times 101 at 5050. Okay. Okay, so next, let us see the next question. So in the formula 2 to the power n factorial pn sec theta. So not sec, sorry, cosec theta. Okay, equals to k theta of times d theta to the power n cot to the power 2n theta. So then the value of k pi by 6 equals to what? This is what we have to calculate. Okay. Okay. So Pnx is what? Again, I am writing the same formula. Okay. So this is equals to 2 to the power n time n factorial. Pnx equals to one thing, we put x equals to cosec theta because we have to find Pn at cosec theta. So x equals to cosec theta. So d dx equals to d theta dx d theta, right? And then dx d theta inverse d theta. So what is dx d theta? Can you tell me? Minus cosec theta cot theta, right? That way, so that is, you are right. That is, we can write cos theta by sine square theta. Yeah, good, good, good. Uh, and so this is dx d theta. So this is your minus sine square theta by cos theta and d theta. Now is it correct? So now, so come back to your this Pn cosec theta equals to C. So this is dn dxn. So that is what you have to write, minus sine square theta by cos theta d theta. So you are transforming, okay, n, and x square minus 1 is what? Cosec square theta minus 1. Cosec square theta minus 1 equals to what? Cot square theta, right? So cot to the power 2n theta. Okay, cosec square theta minus cot square theta. Here cosec square theta minus 1 is cot square theta, so cot to the power 2n theta. Okay, and so compare this with this, all are okay. 2 to the power n time n factorial Pn cosec theta equals to k theta time d d theta n and cot to the power 2n theta. So your k theta is what we are getting minus sine square theta divided by cos theta, and you have to find k pi by 6. Yes, yeah, and so what is sine square pi by 6 and cos pi by 6? So this is sine square pi by 6 is 1 by 4, and this is root 3 by 2, and this is basically minus 1 by 2 root 3. Correct? This is the answer. Okay. Okay, this is a like similar problem in assignment. There is a similar problem in assignment. Okay, you can check. Okay, I think it will help you to solve the assignment problems. Next question: in which of the following cases is the series n equals to 3 to infinity Cn Pnx convergent in L2 minus 1 1? So option A is Cn equals to log n to the power 3 by 2, Cn equals to log n to the power n to the n log n by n to the power 3 by 2. Option C, Cn equals to n by log n square. Option D, 1 by log n to the power 3 by 5. Okay, so we actually have seen in lecture, so this sum Cn and Pnx, this convergence is convergent if this sum Cn square by n is convergent. Okay, so now just apply. So option A, right? So this is given Cn by log n to the power 3 by 2. So what is sum? This is 1 by n log n to the power Cn square, so cube. So whether this series is convergent or not? Yes. So this is convergent, right? Because you know this log n you can bound some constant time into the power epsilon. Ah no, this is not convergent actually. Sorry, this is divergent. I think you have seen. So this sum 1 by n to the power a log n to the power b. So this is conversion if a greater than 1. So see, this is this can be done by Cauchy condensation test. Okay, you can check. And for b, Cn equals to log n by n to the power 3 by 2. So sum Cn square by n log n square. So n time n n to the power 3. So this is absolutely convergent because log n you can bound some epsilon n to the power epsilon, and this is n to the power 4. So this is bigger. Okay, so this is convergent. Okay, no problem. So log n you can bound by n to the power epsilon. So this is 1 by n to the power 4. So this sum basically 1 by n to the power 4 minus epsilon. So this is convergent. Okay, and for C, Cn equals to n by log n whole square. For this case, Cn square by n is what? So this is n square divided by n log n to the power 4. So this is not convergent at all because bigger is sorry, in numerator this is bigger. Okay, so this is divergent. Log is smaller than n, right? Yeah, that's why. And any power if you take, then also this is less than n. Okay. And for part D, so Cn is 1 by log n to the power 3 by 5. Cn square divided by n. So this is basically 1 by n time log n to the power 3 by 5 into 3 by 5, so 6 by 5. And this is also divergent by Cauchy condensation because this is only n to the power 1 divergent. So option A and B, sorry, not A and B, only B is correct. Okay, okay, okay. So last question, question 6. The set of Q linear combination of legendary polynomial is dense in LP minus 1 1 for option A p equals to half, option B p equals to 1, option C p equals to infinity, option D for all p belongs to 2 to infinity. Okay, so this is a this simple question. So the theorem is, so this is in lecture video. Okay, this is big proof, so I cannot uh, proof now. Okay, you can check, and if you have any problem, you can ask me. Dense in LP for all. So from Oyster approximation theorem, it will come only. Okay, so P belongs to 1 to infinity. So P equals to 1, it holds. This is not holds, does not holds. Okay, and this does not hold. and this holds. So B and D is correct. B and D are correct. Okay. Hi. Uh, am I audible, right? Okay. So please solve the assignment problem. Okay, and submit it timely. And then we will join in next week. Okay, at the same time. Do you have any issue? Okay, if you have any problem, you can ask now. Okay, okay. Thank you. Okay. In PhD, in my PhD, so number theory. Yeah. Do you know about it? So, yeah, 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 yeah. Hmm. Hmm. Srinivasan. Exactly, exactly. You are right. There are lots of interesting thing in number theory. Okay. If you have time, so you can explore. Okay. 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 Then yeah, yeah. I'll share you. Okay. I'll share it. I'll share you definitely. Okay. In your mail. Okay. Yes, yes, yes. So you can write here in chat box. Oh, wait, wait. Okay. Okay. Now only you just put. Okay. Okay. Thank you. I'll share. Okay. 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 Thank you. So please join in next week. Okay. 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 Thank you.